In this section, 11.5, we're going to continue on with computing probabilities. We're going to look at permutations, combinations, and the fundamental counting principles. So 11.1 through 11.3, those counting methods. We're going to apply those to probabilities in this section. This is actually not a very long section. So the first example we're going to look at is how you would use permutations in a probability. Example 1, let's say there's 6 acts performing at a talent show. So we have a singer, a dancer, a comedian, an acrobat, a violinist, and a fire eater. Let's say that we're going to figure out how to schedule these performances in the talent show. So it's going to be a random selection. We're going to put each act's name on a piece of paper, throw it into a hat, and then the order in which we draw out the names will determine the order that the acts perform. The question is, what is the probability that the dancer performs first, the singer fourth, and the comedian last when we pull these names out of the hat? So again, we're looking for a probability, which means a fraction. We have to figure out what's going to go in the numerator and what's going to go in the denominator. The numerator is our particular event. And the particular event that we're looking for is dancer first, singer fourth, comedian last. So oftentimes when I'm trying to figure out my event or my sample space, especially with this particular case, which is a permutation. Remember, in a permutation, the order matters. So I'll often make little blanks, 1, 2, 3, 4, 5, 6, to represent my 6 acts that I'm going to schedule. So we're going to have a first performance, second, third, and so on. And I'm going to be looking at the event here. I'm going to be looking at the numerator of my fraction when I figure out my probability. So if the dancer has to perform first, I only have one choice on who's going to perform first. That's the dancer. So second, third, fourth. If the singer has to perform first, then I only have one choice for who's going to perform fourth. Sorry, not first, fourth. And that would be the singer. So we have our fifth act, and then the last would be the sixth. The comedian has to go last, so I only have one choice there. It has to be the comedian. So I've scheduled these 3 acts. Now I have 3 acts remaining. When I choose who's going to perform second, I have 3 choices. Once it's chosen, then there's only 2 acts left to schedule. So I only have 2 choices for who's going to go third. Once I pick who's going to go third, I only have 1 choice for who's going to go fifth. When we multiply all of this across, it's going to be equal to 6. Now in the denominator, it's all possible outcomes. So it would be all possible scheduling of the 6. Again, if you have 1, 2, 3, 4, 5, 6 performances, you have 6 choices for who's going to go first. Once you've chosen, you only have 5. It's going to turn out to be that 6 factorial. Then once you've chosen your second performer, you have 4, and so on. So this 6 factorial, which would be the sample space or the denominator, is going to be 720. Which means our probability, which is a fraction, is going to be the event 6 over the sample space 720, and that reduces to 1 over 120. So that's the only example I'm going to do with the permutation. Let's go ahead and look at an example where we have combination. Example 2, Florida's lottery game lotto is set up so that each player chooses 6 different numbers from 1 to 53. If the numbers chosen match the numbers drawn, then the player wins or shares the top cash prize. The order that the numbers are drawn does not matter. So since the order that you draw your numbers does not matter, this is an example of a combination. But it's still just one group. We're still just choosing from this set of numbers from 1 to 53. Hawaii doesn't have a state lottery. It comes up once in a while in the legislature, but it's always pushed down. And the reason why is because it tends to target lower income. Yes, a lottery will bring in state revenue, but at what cost? Well, the cost is to the lower income. because those are the people that really want to win that $1 million prize. So they're the ones that are really going to go out there and buy tickets when they actually should be saving that money or spending it on something that's more important. But Florida does have a lotto. In part A, it says, with one lotto ticket, what is the probability of winning the prize? Okay, so think about this. In how many ways can you win? That's our event. Well, you bought one ticket. Since all 6 numbers have to match, for part A, there's only one way that you can win. So in the denominator, that's all possible outcomes when choosing the 6 numbers. Okay? Since order doesn't matter, this is a combination where out of the 53, you're choosing 6. And gosh, I hope this is right in my calculator. What I have is 1 over 2, 2, 9, 5, 7, 4, 8, 0. Now, if you wrote this as a percent, well, as a decimal, it's something like 0.0000000044. It's so small. It's essentially 0. This is roughly 0% chance. So probability-wise, if you buy a ticket, you have essentially 0% chance to win. It's all just a matter of luck. Let's look at part B. Let's make it more interesting. Let's say that you purchase 5,000 tickets. So if you purchase 5,000 tickets, that should help your chances because now you have 5,000 ways that you could win. The denominator is still the same. It's still out of the 53 numbers, you're choosing 6 and it's a combination. So you have 5,000 over the 22957,480. As a decimal, that's essentially 0.00022. Think about that. Move the decimal over 2 places. That's 0.022%. Again, that's still approximately 0% chance. And here I've spent $5,000. And I still have a 0% probability of winning the lottery. Let's look at another example. Example 3 has another type of lottery. It's called a Powerball. And that's in some states where there's actually 2 sets of numbers that you choose from. So in one drum, so you have these 2 drums. In one of the drums, you're choosing 5 numbers from 1 to 69. And then you choose your Powerball number, which would be the other drum. And that's 1 to 26. So you're choosing 5 numbers and you have 69 numbers to choose from. And then you're choosing 1 number and you have 26 to choose from. So you have 2 different groups of numbers. The order that you choose does not matter. However, a player wins the jackpot if all of the white balls, so the white balls would be the 69 that you choose from. So if all fall white ball numbers match and the red ball, which is your Powerball number chosen from the 1 to 26 numbers, if they all match, if all 6 match. With one Powerball ticket, what is the probability of winning the jackpot? So again, we only have 1 ticket, so there's only one way we can win that jackpot. If all 5 white ball matches and the red ball matches. Since we're looking at 2 groups, we have to be careful. We have to look at how many ways we can choose the 5 numbers from the white balls and how many ways we could choose the 1 number from the red balls. So the 2 groups would be white and red. Again, order doesn't matter. So out of the 69 white balls, it's a combination where we're choosing 5. Out of the red balls, there's 26 numbers to choose from, combination where we're choosing one. So since we have two different groups, then now we use the fundamental theorem, or the fundamental counting principle from 11.1, where we multiply those two groups together. So 1 over 69 combination 5 times 26 combination 1. That would be 1 over, again, double check me on this, it's 292201338, which is 0.00000, a lot of zeros, 3, 4 at the end, and that's approximately 0%. Well, let's go away from gambling with lottery tickets and go on to our last example. This is pretty short. All the problems are kind of basically the same. Example 4, we have a club. It consists of 6 men and 5 women. 3 members are going to be selected at random to attend a conference. So we want to find the probability that the selected group consists of part A, 3 women, or part B, 2 men and 1 woman. Okay, so there's a couple things going on here. In this club, there's 6 men and there's 5 women. So there's these two groups. We have a total of 11 people in this club. And we're choosing 3 from the 11 to attend a conference. Since we're trying to find a probability, we have a fraction. So in how many ways can we choose 3 women? That would go on the top. On the bottom, it's how many ways we can just choose 3 people from the total of 11. So in the denominator, it's a combination because the order we choose the people doesn't matter. It's going to be 11C3. But the numerator, we have to be careful. We're only choosing from the women. We're not concerned with the 6 men. We're only looking at how many ways we can choose 3 from the 5 women. So it's going to be 5C3. And you would do these separately in your calculator where the numerator would be 10. The denominator is 165. So again, we have to reduce. It looks like it's going to be dividing by 5332 over 33. Let's try one more. We want to find the probability of choosing 2 men, 1 woman. So again, it's a probability. In the bottom, it's all ways we can choose 3 out of the 11. So the denominator is still 11C3. But in the top, we have to be careful because we have to look at how many ways we can choose 2 men and how many ways we can choose 1 woman. So there's 2 groups there. So to choose the men, I'm choosing 2 out of 6. Order doesn't matter, so it's 6C2. To choose the women, I'm choosing 1 woman from 5, so it's 5C1. And then you would multiply those 2 groups together to get your numerator. So 6C2 times 5C1. That gives me, I'll do it down below here, 15 times 5, and the denominator is still 165. So I get 75 over 165, which I would reduce to 5 over 11. Okay, and that's it for this section. In 11.6, 11.7, we're going to explore probabilities in greater detail. So notice that they're getting a little bit complicated. And that's going to continue, sorry, but that's it for this section.